Today, I'll be discussing feedback control systems. This topic is presented by Rajanikant A. Vimetri from the Department of Electrical Engineering at Rajarambapu Institute of Technology, Rajaramnagar. Our institute is an empowered autonomous institute, approved by AICTE and affiliated with Shivaji University Kolhapur. Throughout this presentation, I'll guide you through the fundamental concepts and applications of feedback control systems, which are essential in electrical engineering and many other fields. If you have any questions or need further clarification, please feel free to reach out via the provided email or phone number. Let's dive into the exciting world of control systems. On this slide, we're focusing on control system engineering, which is a crucial field in engineering that deals with designing and managing systems to behave in a desired manner. Essentially, control systems help us automate processes and maintain stability in various applications, from simple household appliances to complex industrial machinery. By understanding control system engineering, we can improve efficiency, accuracy, and safety across many technologies. This foundation will be important as we dive deeper into the principles and applications throughout the presentation. By the end of this course, students will have achieved several important outcomes. First, they will be able to represent physical systems using mathematical models, which is fundamental for analyzing and designing control systems. They will also learn how to calculate time domain specifications for second-order systems, giving them insight into system performance like stability and response time. Additionally, students will be skilled in analyzing different systems through both time and frequency domain tools and techniques, enabling a comprehensive understanding of system behavior. The course also covers a comparison of various controllers and compensators, helping students determine the best approach for different control challenges. Lastly, students will apply state space techniques to analyze and understand multi-input multi-output, or MIMO systems, which are essential in more complex control scenarios. These outcomes ensure a well-rounded grasp of feedback control systems, equipped for practical application and advanced study. This structured mapping ensures alignment between what we learn, the broader program goals, and the syllabus timeline. In this topic, we dive into the concept of stability, which is crucial for understanding how systems behave over time. We'll explore how the location of poles and zeros in a system affects its stability, and introduce the Routh Hurwitz criterion as a method to determine stability systematically. Additionally, we'll use the root locus method to analyze gain margin, phase margin, and overall system stability through practical examples. By the end of this topic, you'll be able to explain the time response characteristics of both first and second order systems. You'll learn how to determine the steady-state error for different system types and understand how this relates to overall system performance. We'll also cover how to compute key time domain specifications like rise time, settling time, peak time, and overshoot, which are essential for characterizing second-order systems. Furthermore, you'll be equipped to evaluate how changes in system parameters affect the responses of both open-loop and closed-loop systems, helping you assess system sensitivity. Finally, we'll analyze the crucial role of feedback in influencing system stability, improving response, and enhancing disturbance rejection. This comprehensive understanding will give you a solid foundation to analyze and design stable, responsive control systems. When we talk about the concept of stability in an LTI system, it's crucial to understand two key ideas. First, the system is considered stable if, whenever it receives a bounded input, its output remains bounded as well. This means the system doesn't produce unbounded or runaway responses when given reasonable inputs. Second, in the absence of any input, the output should naturally settle down toward zero. This point is called the equilibrium state. This behavior, where the output returns to zero regardless of where it started, is known as asymptotic stability. Together, these conditions define what we call BIBO, or bounded input bounded output stability, which is a very important measure of how well the system performs in response to inputs over time. When we talk about stability in a system, what we mean is whether the output remains controlled over time. Simply put, if the output stays within a certain range and doesn't spiral out of control, the system is considered stable. This is usually defined as producing a bounded output when given a bounded input. If the output goes beyond control, the system is labeled unstable. Now, based on how systems behave in terms of stability, we can classify them into three categories. First, an absolutely stable system, which means it remains stable under all conditions. Then, we have conditionally stable systems, where the system's stability depends on certain parameters or conditions being met. Lastly, there are marginally stable systems, which are right on the edge, neither moving toward stability nor instability, often oscillating without growing unbounded. Understanding these classifications helps us predict and control system behavior more effectively. When we talk about an absolutely stable system, we mean a system that remains stable for every possible value of its components. For an open-loop control system, this absolute stability occurs if all the poles of its transfer function are located in the left half of the S-plane. This essentially means the system's response will not grow uncontrollably over time. The same principle applies to closed-loop control systems. Their absolute stability requires all poles of the closed-loop transfer function to also be in the left half of the S-plane. This ensures that the system will behave predictably and return to equilibrium after any disturbance, regardless of parameter variations. So, in essence, the position of these poles in the S-plane is a key indicator of absolute stability in any control system. A conditionally stable system is one that remains stable only within a specific range of its component values. In other words, the system's stability depends on certain parameters staying within particular limits. If these values change beyond that range, the system may become unstable. Understanding this concept is crucial because it helps us design systems that perform reliably under varied conditions, ensuring safety and functionality. So, when we talk about a conditionally stable system, we're acknowledging that stability isn't absolute but depends on maintaining the right conditions. A marginally stable system is one that produces an output signal with a constant amplitude and constant frequency of oscillations when given a bounded input. This means the system neither diverges nor settles to zero, but continues to oscillate steadily. In terms of the system poles, for an open-loop control system to be marginally stable, at least two poles of its open-loop transfer function must lie exactly on the imaginary axis of the complex plane. Similarly, for a closed-loop control system, marginal stability occurs when two poles of its closed-loop transfer function are located on the imaginary axis. This positioning of poles indicates that the system is on the edge between stability and instability, where oscillations don't die out but also don't grow uncontrollably. Understanding this concept is crucial for analyzing system behavior and designing controls that avoid unwanted oscillations. When we talk about stability in a system, it all comes down to the roots of the characteristic equation. If every root has a negative real part, the system is stable, meaning it will respond predictably and settle over time. On the other hand, if even one root has a positive real part or if there's a repeated root on the imaginary axis, what we call the JW axis, the system becomes unstable, which means it could grow unbounded or behave erratically. Then there's the case of marginal stability, where all roots have negative real parts except for one or more non-repeated roots exactly on the JW axis. Here, the system neither grows nor decays, but maintains a steady oscillation. Understanding these root conditions is crucial for predicting and controlling system behavior. When classical control methods were first developed, determining the poles and zeros of higher-order systems was quite challenging. This was mainly because there were no tools like MATLAB or other computer software to assist in these calculations. Without these tools, engineers had to rely on complex mathematical techniques, which could be time-consuming and prone to errors. So, the question arises, how did they check system stability under these circumstances? Was there an alternative method available to analyze stability without explicitly finding all poles and zeros? This sets the stage for exploring stability analysis techniques suited for higher-order systems, especially before the advent of modern computational tools. Let's talk about the Routh stability criterion. This criterion allows us to determine the number of closed-loop poles that lie in the right half of the S-plane without having to solve for the poles explicitly. Essentially, it gives us a way to assess system stability by examining the characteristic equation's coefficients. A key point here is that for a system to be stable, all the coefficients of the characteristic equation must be present and must be positive. If any coefficients are 0 or negative, it indicates the presence of poles in the right half plane, which means the system is unstable. This method is particularly useful because it simplifies the stability analysis significantly. The Routh Hurwitz stability criterion involves two key conditions, a necessary condition and a sufficient condition for stability. First, the necessary condition must be met for the control system to even be considered stable. If this condition is not satisfied, we can confidently say that the system is unstable. However, meeting the necessary condition alone doesn't guarantee stability, it just means the system might be stable. This is where the sufficient condition comes into play. It helps us determine definitively whether the control system is stable or not. So, to fully assess stability, both conditions play crucial roles, with the sufficient condition providing that final confirmation. Now, let's discuss the necessary condition for Routh Hurwitz stability. For the system to be stable, a key requirement is that all the coefficients in the characteristic polynomial must be positive. This condition ensures that all the roots, or the poles, of the characteristic equation have negative real parts, which is crucial for system stability. It's important to remember that the characteristic equation should be of order n, and importantly, no term should be missing in this equation. That means none of the coefficients can be zero. If any coefficient is zero or negative, the system cannot be stable according to this condition. So, in summary, positivity of all coefficients in the characteristic polynomial is a necessary condition for the system to be stable, linking directly to the location of the roots in the left half of the complex plane. Now let's focus on the sufficient condition for Routh Hurwitz stability. The key point here is that every element in the first column of the Routh array must have the same sign. In other words, all these elements should be either positive or all negative. This uniformity in sign indicates that the system is stable according to the Routh Hurwitz criterion. If the signs differ, the system will have poles in the right half of the complex plane, leading to instability. So, maintaining the same sign across the first column is essential for ensuring system stability. Now, let's focus on an important step in analyzing control systems, writing the characteristic equation of the closed-loop transfer function. This equation is crucial because it helps us determine the stability and dynamic behavior of the system. Essentially, the characteristic equation comes from the denominator of the closed-loop transfer function when set equal to 0. By solving this equation, we can find the system poles, which tell us if the system will behave as desired or if it might become unstable. Understanding this procedure is key before moving forward with any design or analysis, so keep this in mind as we continue. Now, let's focus on evaluating the b's in this procedure. It's important to note that these b's are different from those in the transfer function we might have seen earlier. We continue evaluating the b's until all the remaining values are 0, ensuring we've captured all necessary coefficients. The key method here is cross-multiplying the coefficients from the previous two rows to find the new b's. Once determined, we update the array with these new values. We then use the same approach to find the next set of coefficients, the c's, d's, e's, and so on, always cross-multiplying the coefficients from the two preceding rows. This process is repeated systematically until the nth row of the array is fully completed. This step-by-step cross-multiplication and updating ensures that all necessary coefficients are accurately calculated for the analysis at hand. Here, we're looking at an illustration of the procedure. This visual representation helps us understand the step-by-step process clearly. As we go through this, focus on how each step connects to the next, ensuring a smooth flow. The key takeaway is to grasp the sequence and how each part contributes to the overall operation. This understanding is crucial for applying the procedure effectively in practical scenarios. The Routh stability criterion tells us that the number of poles of the closed-loop transfer function in the right half of the S-plane equals the number of sign changes in the first column of the Routh array. This is crucial because it directly indicates system stability. Simply put, for the closed-loop system to be stable, all coefficients of the characteristic equation must be present and positive. Additionally, every term in the first column of the Routh array must have the same sign. If this condition is satisfied, we can confidently say the system is stable. This criterion provides a straightforward way to assess stability without explicitly calculating the roots of the characteristic equation. On this slide, we're focusing on applying the Routh stability criterion to determine the stability of a system characterized by its characteristic equation. The key idea here is to use the Routh array, a systematic method that helps us examine the number of roots with positive real parts without actually solving for them. By constructing this array and analyzing the sign changes in the first column, we can quickly assess whether the system is stable. This example will walk us through that process step by step, illustrating how the criterion can provide a clear and efficient way to check system stability. Here, we're going to examine the stability of the polynomial fs equals s cubed plus 6s squared plus 11s plus 6 set equal to 0. This is a classic example used to apply the Routh stability criterion, which helps us determine if all the roots of this polynomial lie in the left half of the S-plane, indicating a stable system. We'll walk through the process of constructing the Routh array and analyze the signs of the first column to conclude the system's stability. This approach is particularly useful because it allows us to assess stability without explicitly calculating the roots, saving time and effort especially for higher-order polynomials. Let's analyze the stability of the system using Routh stability criterion based on the characteristic equation fs equals s to the power of 4 plus 2s cubed plus 4s squared plus 6s plus 8 is equal to 0. The key goal here is to determine how many poles lie in the right half of the S-plane, which directly indicates system stability. Using Routh's criterion, we build the Routh array from the coefficients of the characteristic equation. If any sign changes occur in the first column of this array, it means there are poles in the right half-plane and the system is unstable. By carefully evaluating this equation, we check for the number of sign changes. This method provides a straightforward way to assess stability without explicitly solving for the roots, making it a powerful tool for control system analysis. Now, let's talk about the two special cases that can occur when constructing the Routh array. The first special case happens when the very first element of any row in the Routh array is 0. This can create complications in the process because we can't proceed with the usual calculations for the next row without adjusting for this 0 element. The second special case occurs when all the elements in a particular row are 0. This situation indicates the presence of symmetrical roots or repeated roots, and it requires a different method to move forward in the stability analysis. Both of these cases need to be handled carefully to correctly determine the system's stability using the Routh criterion. Now let's take a closer look at some special cases that can arise when constructing the Routh array. These cases are important because they require us to adapt our standard procedure to correctly determine system stability. One common special case occurs when a row in the Routh array consists entirely of zeros, which indicates the presence of symmetric roots or repeated roots on the imaginary axis. Another special case happens when the first element of a row is 0 but the row is not entirely 0. In this situation, we typically replace that 0 with a small positive number, often denoted as epsilon, to proceed with the analysis. Understanding how to handle these special cases is crucial for accurately assessing the stability of control systems using the Routh criterion. Here, we're going to analyze the stability of a control system by examining its characteristic equation, which is given as f of s equals s to the fourth plus 2s cubed, plus s squared, plus 2s, plus 1 equals 0. This equation forms the basis for constructing what's called the Routh array, a method used to determine system stability without explicitly solving for the roots of the equation. Understanding these special cases in the Routh array is crucial because they help us identify scenarios where standard stability tests might fail or require additional steps, such as the presence of 0 entries in the array or special patterns that could indicate marginal stability. I'll guide you through how to approach these cases and ensure accurate stability analysis. Here, we're looking at a special case in the Routh array method, involving the polynomial equation f of s equal to s to the fifth power plus 2s to the fourth, plus 3s cubed, plus 4s squared, plus 5s, plus 6, set equal to 0. The question we're addressing is how many poles of this system lie in the right half of the s-plane. Identifying poles in the right half-plane is critical because it indicates system instability. In cases like this with higher-order polynomials, the Routh array helps us determine stability without explicitly calculating the roots. By constructing the Routh array and examining sign changes in the first column, we can find the number of roots with positive real parts, thus telling us how many poles are in the right half-plane. This approach saves time and provides essential insights into system behavior. Here, we're looking at a special case in the Routh array where all the elements of a particular row become 0. This situation is significant because it indicates the presence of roots that are purely imaginary or symmetrical about the imaginary axis. When this happens, it complicates the stability analysis using the Routh Hurwitz criterion. Let's consider the characteristic equation given, fs equals s to the fifth plus 3s to the fourth plus s cubed plus 3s squared plus s plus 3. If, while constructing the Routh array for this polynomial, a complete row of zeros appears, it signals that the system has roots lying on the imaginary axis, which means the system is on the verge of instability. In other words, the system is marginally stable and may exhibit sustained oscillations. In such a case, the standard Routh criterion doesn't directly apply, and additional methods, such as forming an auxiliary polynomial from the row above and examining its roots, are used to determine the stability of the system. This special case requires careful handling to accurately evaluate the system's behavior. Here, we're looking at a special case in the Routh array where the characteristic equation is given as s to the fifth plus 3s to the fourth plus s cubed plus 3 squared plus s plus 3 equals 0. When we form the Routh array from this polynomial, we observe two sign changes in the first column. This is a critical point because the number of sign changes tells us about the stability of the system. Specifically, two sign changes indicate that the system has two roots with positive real parts, meaning the system is unstable. So, despite the complexity of the equation, this sign change criterion gives us a straightforward way to assess stability quickly and effectively. Here, we are analyzing the stability of the system represented by the characteristic equation f of s, which is s to the 6th power plus 2s to the 5th plus 8s to the 4th plus 12s cubed plus 20s squared plus 16s plus 16 equal to 0. The stability of the system depends on the location of the roots of this polynomial in the complex plane. If all roots have negative real parts, the system is stable. Otherwise, it could be unstable or marginally stable. Our goal is to comment on the stability by examining the coefficients and possibly applying methods like the Routh Hurwitz criterion or other stability tests to determine if any roots lie in the right half of the S-plane. This analysis is crucial because it tells us whether the system's response will settle down over time or grow uncontrollably. Let's take a closer look at the stability of the system described by the characteristic equation Fs equals s to the power of 6 plus 2s to the power of 5 plus 8s to the power of 4 plus 12s cubed plus 20s squared plus 16s plus 16 equal s0. Stability in control systems depends on the location of the roots of this polynomial. For the system to be stable, all roots must lie in the left half of the complex plane, meaning they must have negative real parts. By analyzing the 6th-degree polynomial, we aim to determine whether this condition is satisfied. Various methods, such as the Routh Hurwitz criterion, can be used to assess stability without explicitly finding the roots. It's important to look for any sign changes or patterns in the coefficients that could indicate poles in the right half plane, which would signal instability. So, the focus here is on understanding whether the system's behavior will remain steady over time or if it might oscillate or diverge due to unstable poles. Let's look at the range of values for the gain k that ensure the closed-loop system remains stable. To analyze this, we start with the closed-loop transfer function and extract the characteristic equation from it. Using this equation, we form an array of coefficients which helps us apply the Routh stability criterion. The key point here is that for the system to be stable, k must be positive, and every element in the first column of the Routh array must also be positive. This ensures no sign changes occur, which would indicate poles in the right half of the complex plane and instability. By carefully examining these conditions, we can pinpoint the exact range of k values that maintain stability. On this slide, we will look at some examples to better understand the Routh stability criterion. This criterion is a powerful tool used in control systems to determine the stability of a system without actually calculating the roots of the characteristic equation. By constructing the Routh array, we can quickly assess whether any roots lie in the right half of the S-plane, which would indicate instability. Through these examples, I'll guide you step by step on how to form the Routh array and interpret the results, making it easier to apply this concept in practical scenarios. Let's dive into these examples and solidify your understanding of the Routh stability criterion. The root locus is a graphical method used to find the poles of a closed-loop system based on the poles and zeros of its open-loop system. Essentially, it shows us how the system's closed-loop poles move in the complex plane as we adjust a gain parameter from 0 to infinity. This technique was developed in the late 1940s by Walter R. Evans. It's particularly helpful because it allows us to visualize how the roots of a system's characteristic polynomial evolve as we change a single scalar value, like the gain, helping us understand system stability and behavior more intuitively. Here, we're looking at the root locus of the system, which is a graphical way to analyze how the closed-loop poles change as the gain k varies from 0 to infinity. The closed-loop transfer function is shown, and it's important to focus on the characteristic equation since the locations of the closed-loop poles are the zeros of this equation. As k changes, the positions of these poles move in the complex plane. The table below summarizes key rules for sketching the root locus, indicating how these pole locations shift with increasing gain. Understanding this movement helps us predict system stability and performance for different gain values. Essentially, root locus plots provide valuable insight into how the feedback gain influences the dynamics of our control system. Now let's delve into the rules of the root locus method, which is a powerful graphical tool used in control system design. The root locus helps us understand how the roots of a system's characteristic equation change as a particular parameter, commonly the gain, varies. By following specific rules, we can accurately sketch the root locus plot. These rules guide us on how to determine the starting and ending points of the loci, their paths on the complex plane, and where they intersect the real axis. Understanding these fundamentals allows us to predict system stability and transient response behavior as gain changes, enabling effective controller design. So, mastering the root locus rules is essential for anyone looking to analyze or design control systems with confidence. Now let's talk about the key rules of root locus. These rules help us understand how the roots of a characteristic equation move in the complex plane as a particular system parameter, usually gain, changes. Root locus is a powerful graphical method in control system design, and by following these rules, we can predict system stability and performance. We will cover things like identifying starting and ending points of the loci, the behavior on the real axis, breakaway points, and asymptotes. Understanding these principles is crucial for effectively using root locus in analyzing and designing control systems. Here, we'll take a closer look at typical sketches of root locus plots. These sketches help us visualize how the roots of a system change as we vary a particular parameter, usually the gain. Understanding these plots is crucial because they give us insight into system stability and transient response. By studying the shape and direction of the loci, we can predict how the poles move in the complex plane, which ultimately impacts the behavior of our control system. This foundational knowledge will be essential as we analyze more complex systems and their stability characteristics. Here, we have a practical example of a root locus plot. The root locus is a powerful tool that helps us understand how the roots of a system change as a particular parameter, usually the gain, varies. By analyzing this plot, we can predict the stability of the system and how it will behave dynamically. This example will walk us through the steps of constructing the root locus and interpreting its key features, such as how the poles move, where they settle, and what that means for system performance. It's essential to grasp these concepts to design and tune control systems effectively. This slide is currently empty, so let's move to the next slide. This slide is currently empty, so let's move to the next slide. This slide is currently empty, so let's move to the next slide. Let's look at this root locus example. We're given a closed-loop transfer function with 3 poles and 0 zeros. Since the number of poles, which is 3, is greater than the number of zeros, the number of branches in the root locus will be equal to the number of poles, so we have 3 branches. Next, the angle of the asymptotes is important. These angles are determined based on the difference between the number of poles and zeros, which is 3 minus 0, giving us 3 minus 1 in the expression for the angle. The angle Q ranges from 0 up to P minus Z minus 1, which in this case translates to values between 0 and 2. Finally, the centroid, where the asymptotes intersect the real axis, is also a key point in the analysis, although the specific formula or value isn't given here. Understanding these concepts helps us plot the root locus accurately, which is crucial for stability and controller design. Here, we are analyzing the breakaway point in the root locus plot. The value of the root at minus 7.88 falls outside the predicted section for the breakaway point, so it is invalid. Instead, the valid breakaway point is at s equals minus 2.113. To confirm this, we substitute s equals minus 2.113 into the characteristic equation and solve for k. The value of k we obtain is positive, which means this root is indeed valid. This positive k indicates the system's gain at which the root locus breaks away from the real axis, helping us understand the stability and behavior of the system as the gain changes. Here, we're focusing on finding the point where the root locus crosses the imaginary axis. To do this, we start with the characteristic equation and then form the Routh array, expressed in terms of the gain k. The goal is to determine CMAR, which is the value of k that causes one row of the Routh array to become all zeros, excluding the first row, S0. Looking specifically at the S1 row, we have the equation 750 minus k equals 0. Solving this gives us CMAR, or Km, equal to 750. This value indicates where the root locus intersects the imaginary axis. Since the poles in this example are not complex, we don't need to consider angles of departure. So, the key takeaway is that by using the characteristic equation and Routh array, we can pinpoint the exact gain value where the system transitions, helping us analyze stability effectively. Here, we're looking at an example of a root locus, which is a graphical method used to analyze and design control systems. The root locus shows the paths of the poles of a closed-loop system as a particular parameter, typically the gain, varies. Understanding the complete root locus helps us predict system stability and dynamic response. By examining this plot, we can determine how the poles move in the complex plane, which directly influences system behavior like oscillations and damping. This visualization is crucial for designing controllers that ensure the system performs reliably and meets the desired specifications. In this example, we're asked to sketch the root locus and predict the system's stability. We start with the given poles at s equals minus 1 plus j and minus 1 minus j, meaning our system has 3 poles and no zeros. Since the number of poles, 3, is greater than the number of zeros, 0, the number of root locus branches equals the number of poles, which is 3. Looking at the pole 0 plot, we see that one branch originates from s equals 0 and moves toward negative infinity. This tells us that the system's behavior will include a path extending far into the left half of the complex plane, which is generally a good sign for stability. Also, note that there are no breakaway points in this plot, meaning the roots do not cluster or split in the middle of the real axis. To analyze further, we look at the centroid, which gives the center point where the asymptotes intersect on the real axis, and the angle of asymptotes, which indicates the directions these branches take as they move toward infinity. Understanding these components helps us predict how the system poles move with varying gain and ultimately assess stability. Here, since the branches move leftward and no poles cross into the right half plane, the system tends to be stable under these conditions. Here we are examining the breakaway point on the root locus. The candidate point is at s equals -0.67 plus or minus j 0.47. When we substitute this value into our characteristic equation, we find the angle is approximately -164.20 degrees, which is not an odd multiple of 180 degrees. This means that this particular point does not lie on the root locus, and therefore, it is not a valid breakaway point. So, the conclusion here is that s equals -0.67 plus or minus j 0.47 is not where the root locus branches diverge. This helps us refine our understanding of the system's stability and behavior. Here, we're looking at the concept of angle of departure and angle of arrival, which are critical in understanding how signals travel between antennas in wireless communications. The angle of departure refers to the direction in which a signal leaves the transmitting antenna. Conversely, the angle of arrival is the direction from which the signal reaches the receiving antenna. These angles are essential for optimizing signal transmission and reception because they impact the strength and quality of the connection. By accurately measuring and managing these angles, we can improve system performance, reduce interference, and enhance overall communication reliability. Here, we're looking at the angle of departure at the complex pole, which is located at -1 plus j. We denote the angles as phi p1 equals 135 degrees and phi p2 equals 90 degrees. These angles are crucial because they help us determine how the root locus departs from the complex pole at the point -1 minus j. Understanding this departure angle is essential for analyzing system stability and behavior in control systems. Here, we are looking at an important aspect of root locus analysis, the point where the root locus intersects the imaginary axis. This occurs when one of the roots, S1 in this case, is equal to 0. Specifically, when the gain Km is set to +4, S1 reaches 0. By substituting Km equals 4 into our characteristic equation, we can analyze the system behavior at this critical point. Understanding this intersection helps us determine system stability and the range of gains for which the system remains stable. This is a key concept in control theory as it allows us to fine-tune the controller gain to achieve desired performance without compromising stability. Here we have a root locus example, which is a powerful tool for analyzing and designing control systems. The root locus helps us understand how the poles of a system move in the complex plane as we vary a particular parameter, usually the gain. This movement directly affects the stability and response of the system. By studying the root locus, we can predict how changes in gain will influence system behavior and make informed decisions to ensure desired performance. It's essential to grasp this concept because it forms the basis for tuning controllers and achieving stable, efficient control systems. Now, let's talk about how to determine the value of k at any point on the root locus. There are two main ways to do this. First, we have the magnitude criterion. At any point on the root locus, the magnitude of the open-loop transfer function equals 1 over k. By applying this formula, we can calculate the specific value of k at that desired point. This method relies on analyzing the magnitude of the system response at a particular location on the plot. Second, we can use the root locus plot itself. The plot visually represents how the roots move as k changes, so by locating the point S on the root locus, we can directly determine the corresponding k value from the graph. This approach provides a quick visual understanding of the system's behavior for different gain values. Both methods are effective, and choosing between them depends on whether you prefer a formula-based calculation or a graphical estimation. Understanding these allows us to control system stability and performance by selecting the right gain, k. On this slide, we're looking at two important stability measures in control systems, gain margin and phase margin. Gain margin tells us how much we can increase the system's gain before it actually becomes unstable. It's a way to quantify how robust our system is to changes in gain. Mathematically, it's expressed as the factor by which the gain can be multiplied before the system loses stability. Phase margin, on the other hand, measures the additional phase lag required to bring the system right to the edge of instability. It's often calculated from the phase of the system at the frequency where the gain crosses unity. Both these margins give us essential insight into the system's stability and its tolerance to variations, making them critical in system design and analysis. Here are the key references that have informed this presentation. First, we have Norman Neese's book, Control System Engineering, which is a foundational text in understanding industrial control systems. Next, the article, Industrial Control Systems Examples, Types, and Concepts. The automation provides practical insights into different types of control systems and their applications in industry. Muhammad Sarwar's comprehensive introduction on Medium offers a clear overview of control systems concepts, which is very helpful for grasping the basics. Additionally, Achrome Robotics presents an accessible explanation of what control engineering entails. Finally, the Jove article included as a video resource supplements this information with visual demonstrations. These references together give a well-rounded foundation on control system engineering. This slide is currently empty, so let's move to the next slide. Thank you all for your attention and participation. I appreciate your time and interest in this topic. If you have any questions or need further clarification, please feel free to reach out. I'm happy to help.